This article is about the theories and mathematics of climate modeling. For computer-driven prediction of Earth's climate, see Global Climate Model. Climate models use quantitative methods to simulate the interactions of the important drivers of climate, including atmosphere, oceans, land surface and ice. They are used for a variety of purposes, from study of the dynamics of the climate system to projections of future climate. All climate models take account of incoming energy from the Sun as short-wave electromagnetic radiation, chiefly visible and short-wave infrared, as well as outgoing long-wave infrared electromagnetic. Any imbalance results in a change in temperature. Models vary in complexity. A simple radiant heat transfer model treats the Earth as a single point and averages outgoing energy. This can be expanded vertically or horizontally. Finally, atmosphere, ocean, sea ice global climate models solve the full equations for mass and energy transfer and radiant exchange. Box models can treat flows across and within ocean basins. Other types of modeling can be interlinked, such as land use, allowing researchers to predict the interaction between climate and ecosystems. Box models. Box models are simplified versions of complex systems, reducing them to boxes linked by fluxes. The boxes are assumed to be mixed homogeneously. Within a given box, the concentration of any chemical species is therefore uniform. However, the abundance of a species within a given box may vary as a function of time due to the input to the box or due to the production, consumption or decay of this species within the box. Simple box models, i.e., box model with a small number of boxes whose properties do not change with time, are often useful to derive analytical formulas describing the dynamics and steady-state abundance of a species. More complex box models are usually solved using numerical techniques. Box models are used extensively to model environmental systems or ecosystems and in studies of ocean circulation and the carbon cycle. Zero-dimensional models. A very simple model of the radiative equilibrium of the Earth is where the left-hand side represents the incoming energy from the Sun. The right-hand side represents the outgoing energy from the Earth, calculated from the Stefan-Boltzmann law, assuming a model fictive temperature, T, sometimes called the equilibrium temperature of the Earth, that is to be found, and S is the solar constant, the incoming solar radiation per unit area, about 1367 Wm-2. Is the Earth's average albedo, measured to be 0.3. R is Earth's radius, approximately 6.371 times 106 meters. Pi is the mathematical constant. Is the Stefan-Boltzmann constant, approximately 5.67 times 10⁻8 Jk-4m-2s-1. Is the effective emissivity of Earth, about 0.612. The constant pi r2 can be factored out, giving solving for the temperature. This yields an apparent effective average Earth temperature of 288 K. This is because the above equation represents the effective radiative temperature of the Earth. The use of effective emissivity and albedo account for the greenhouse effect. This very simple model is quite instructive, and the only model that could fit on a page. For example, it easily determines the effect on average Earth temperature of changes in solar constant or change of albedo or effective Earth emissivity. The average emissivity of the Earth is readily estimated from available data. The emissivities of terrestrial surfaces are all in the range of 0.96 to 0.99. Clouds, however, which cover about half of the Earth's surface, have an average emissivity of about 0.5 and an average cloud temperature of about 258 K. Taking all this properly into account results in an effective Earth emissivity of about 0.64. This simple model readily determines the effect of changes in solar output or change of Earth albedo or effective Earth emissivity on average Earth temperature. It says nothing, however, about what might cause these things to change. Zero-dimensional models do not address the temperature distribution on the Earth or the factors that move energy about the Earth. Radiative convective models. The zero-dimensional model above, using the solar constant and given average Earth temperature, determines the effective Earth emissivity of long-wave radiation emitted to space. This can be refined in the vertical to a one-dimensional radiative convective model, which considers two processes of energy transport: upwelling and downwelling radiative transfer through atmospheric layers that both absorb and emit infrared radiation. Upward transport of heat by convection. The radiative convective models have advantages over the simple model. They can determine the effects of varying greenhouse gas concentrations on effective emissivity and therefore the surface temperature, but added parameters are needed to determine local emissivity and albedo and address the factors that move energy about the Earth. Effective ice-albedo feedback on global sensitivity in a one-dimensional radiative convective climate model. Higher dimension models. The zero-dimensional model may be expanded to consider the energy transported horizontally in the atmosphere. This kind of model may well be zonally averaged. This model has the advantage of allowing a rational dependence of local albedo and emissivity on temperature. The poles can be allowed to be icy and the equator warm, but the lack of true dynamics means that horizontal transports have to be specified. EMICs. Depending on the nature of questions asked and the pertinent timescales, there are, on the one extreme, conceptual, more inductive models, and, on the other extreme, general circulation models operating at the highest spatial and temporal resolution currently feasible. Models of intermediate complexity bridge the gap. One example is the Climate-3 model. Its atmosphere is a 2.5-dimensional statistical dynamical model with 7.5 degrees times 22.5 degrees resolution and time step of half a day. The ocean is MOM3 with her 3.75 degrees times 3.75 degrees grid and 24 vertical levels. GCMs. General circulation models discretize the equations for fluid motion and energy transfer and integrate these over time. Unlike simpler models, GCMs divide the atmosphere and/or oceans into grids of discrete cells, which represent computational units. Unlike simpler models which make mixing assumptions, processes internal to a cell, such as convection, that occur on scales too small to be resolved directly are parameterized at the cell level, while other functions govern the interface between cells. Atmospheric GCMs model the atmosphere and impose sea surface temperatures as boundary conditions. Coupled atmosphere-ocean GCMs combine the two models. The first general circulation climate model that combined both oceanic and atmospheric processes was developed in the late 1960s at the NOAA Geophysical Fluid Dynamics Laboratory. AOGCMs represent the pinnacle of complexity in climate models and internalize as many processes as possible. However, they are still under development and uncertainties remain. They may be coupled to models of other processes, such as the carbon cycle, so as to better model feedback effects. Such integrated multi-system models are sometimes referred to as either Earth system models or global climate models. Research and development. There are three major types of institution where climate models are developed, implemented and used. National Meteorological Services. Most national weather services have a climatology section. Universities. Relevant departments include atmospheric sciences, meteorology, climatology, and geography. National and international research laboratories. Examples include the National Center for Atmospheric Research, the Geophysical Fluid Dynamics Laboratory, the Hadley Center for Climate Prediction and Research, the Max Planck Institute for Meteorology in Hamburg, Germany, or the Laboratoire des Sciences du Climat et de l'Environnement, France, to name but a few. The World Climate Research Program, hosted by the World Meteorological Organization, coordinates research activities on climate modeling worldwide. A 2012 U.S. National Research Council report discussed how the large and diverse U.S. climate modeling enterprise could evolve to become more unified. Efficiencies could be gained by developing a common software infrastructure shared by all U.S. climate researchers, and holding an annual climate modeling forum. The report found climate models on the web. Dapper, D-chart, plot and download model data referenced by the Fourth Assessment Report of the Intergovernmental Panel on Climate Change, NCAR, UCAR Community Climate System Model, Do-it-yourself climate prediction. Primary research GCM developed by NASA, GISS. Original NASA, GISS Global Climate Model with a user-friendly interface for PCs and Macs. CCCMA modeling.For an interface to retrieve model data. NOAA, Geophysical Fluid Dynamics Laboratory CM2 Global Climate modeling.For and model output data files. University of Victoria Global Climate Model, free for download. Leading researcher was a contributing author to the recent IPCC report on climate change. Vimeo.com/user125233777/videos visualizations of climate models of Earth. Zurich. Bibliography. Ralston, Ian, Norbury, John. Invisible in the Storm. The Role of Mathematics in Understanding Weather. Princeton University Press.